We are going to look at the side topic of holes, which are also called removable discontinuities. Basically, we'll have a graph that looks like we just took one point out of it. What we see, and we're going to connect this with our topic of rational functions, is that when the numerator and the denominator share a factor, something odd happens. For example, we have f of x equals 3 times the quantity x plus 3 squared times x minus 2 times x minus 7 all over x times x minus 2. The numerator has a factor of x minus 2, and so does the denominator. We could imagine that we cancel these two values out, leaving us with 3 times x plus 3 squared times x minus 7 all over x. And to graph this function, we do treat the function as if that's what the function was defined as. But we want to remember to put a hole or a removable discontinuity when x equals 2. Even though we crossed out these two factors, indicating that they could cancel with each other, the fact that your denominator has a factor here means that the function is undefined at x equals 2. And the shared factor merely tells us to put a hole there. Let's graph this. We look at the numerator for our roots. We have a root at -3 and +7. Because the -3 is x plus 3 is squared, we are going to bounce. X minus 7 has an exponent or multiplicity of 1, which means we cross. We then look at the denominator for our vertical asymptote. We have one vertical asymptote at x equals 1, and since there's an implied exponent of 1, then we go to opposite infinities. Since the numerator has a higher degree than our denominator, we see the degree of the numerator is 3, the degree of the denominator is 1. The end behavior is going to make this function look like a quadratic. So on the left side, we're going to go to positive infinity, and on the right side, we'll go to positive infinity. Let's graph this. We know we're coming down from positive infinity. We're going to bounce at this root and go up. We have opposite infinities. That means instead of starting at positive infinity, we'll start down here at negative infinity. We'll come up to our other root and cross. But don't forget, we need to put in a hole. We could plug 2 into our function and figure out what the value could be. We find f of 2, which will equal 3 times 25 times -5 all over 2. We find that f of 2 is -187.5. We have a hole at 2, -187.5. So I'm going to white out the middle of that hole. And that is the sketch of our function. So quick note, we do realize that the limit as x goes to negative infinity is positive infinity. The limit as x goes to positive infinity is positive infinity. We can see that the limit will in fact exist around our hole, but the limit does not exist around our asymptote because we're going to opposite infinities.